Welcome back, everyone. This is the part B of the second part of the Senior 4 Physics Current Electricity Revision series with me, your host, Mr. Mande Dennis. So, I promise you that we will be looking at Ohm's law in this part, and we shall explore now the other sensitive issues when it comes to current electricity. Yeah, actually, there is a story. A certain man wanted to be a lab technician of a certain school. So when he went for the job interviews, he was asked whether he knew Ohm's law. And when he was asked as a good Muganda, he said, Kama wange, omuziro gwange, nedira fumbe. So for him, he thought, when they asked for the Ohm's law, they were asking for Ohm's law. Please, we are not talking about the Ohm's law of Uganda. This is Ohm's law. Ohm is a person. This is a person. So the law that he stipulated. Ohm's law states that the current passing through a conductor is directly proportional to the potential difference across its ends, provided temperature and other physical conditions are constant. So this is Ohm's law, and in the conditions that have to be kept constant apart from the temperature include length of the conductor, cross-section area of the conductor, stress and strain. They have to be constant. And the law is just briefly summarized in this way. The current passing through a conductor is directly proportional to the PD across its ends, provided temperature and other physical conditions are kept constant. That's the expression. And the proportionality symbol can be replaced with an equal sign and a K, where the constant or proportionality has a special name which we call R, resistance R. So we can now quote and write V is equal to IR, where V is the PD, I is the current, and R is the resistance. So what is an ohm? Because the SI unit of resistance, this resistance here is an ohm. So what is an ohm? From here, I guess from the previous definitions, you must be able to tell this. We had said previously that if someone is asking for an ohm, so they're asking for 1 ohm. So when you get 1 ohm, from V is equal to IR, you realize that R is equal to V over I. So when will you get 1 ohm? You'll get 1 ohm here when V is 1 volt, this V is 1 volt, and the I is 1 ampere. So each one of them has to be 1. V, 1 volt, I, 1 ampere, R will become 1. So we define an ohm as the resistance of a conductor such that when a potential difference of 1 volt is applied across its ends, a current of 1 ampere flows through it. Okay, now we are going to describe a simple experiment to verify Ohm's law. Setup, very simple. The setup is simple. You will have a battery, or you can use a cell. These are 2 cells, so this qualifies to be a battery. We have a switch, we have a rheostat, that this is a variable resistor. We have an ammeter, and we have a conductor. This is a resistor actually. These the rheostat, the switch, battery, ammeter, and the conductor are set up in series. You connect them in series. Use the connecting wires as I showed you at the introduction of part 2, subsection A. Now, across the conductor, you connect, across this conductor or the resistor, you connect a voltmeter here to measure the PD, which will keep varying. Because here in this experiment, what matters is simple. You want to know, because Ohm's law, remember we said Ohm's law states that the current through a conductor or passing through a conductor is directly proportional to the PD across its ends, provided temperature and other physical conditions are kept constant. So let's look at this case. We are going to keep varying we are going to keep varying the resistance. So when we vary the resistance here, because this is a rheostat, a resistor variable resistance, we will see what happens to the PD here, the PD reading, and the V. Okay, steps are simple. A battery, an ammeter, a resistor, a rheostat, and a switch S are connected in series. This is supposed to be in. Please just do me a favor and ignore this other big I. So, are connected in series as shown in the circuit above. Okay. A voltmeter is connected across the resistor. Yes, you've seen that. The switch S is closed. The rheostat is adjusted to give the smallest readable current on the ammeter. What do we do next? The current I and the voltage V are read from the ammeter and the voltmeter respectively, and they are recorded. Now the procedure is repeated by adjusting the rheostat, which is a variable resistor, to obtain different values of I and V. All you need are the values of I and V. And then tabulate your results or record your results in a suitable table and plot a graph of V against I. So a graph of V against I is plotted. A straight line through the origin is obtained, hence verifying Ohm's law. So once we obtain a straight line through the origin, it means that I is directly proportional to V. By the way, these are supposed to be of the same size. Don't make this mistake, sorry. V and V, they all have to be of the same size because the SI unit of voltage is a volt, and the abbreviation is a capital V, not a small v. Okay. What are the limitations of Ohm's law? Ohm's law does not apply to semiconductors and gases, and is only obeyed if physical conditions like temperature, strain, stress, as we looked at them, are kept constant. So we are saying, okay, now we have realized that Ohm's law can be obeyed and can be disobeyed. Okay, maybe can be broken, not really disobeyed. So the conductors, we have special conductors which are ohmic, and we have those that are non-ohmic. So ohmic conductors, these are conductors which obey Ohm's law. For them, they obey. Very good conductors. Examples include metal conductors, copper sulphate solution with copper electrodes. Actually, many salts with special electrodes obey Ohm's law, though not all, but many. So if you plot a graph of I against V or V against I for ohmic conductors, you get a straight line through the origin, just like that. I against V, or you can say V against I, you get a straight line through the origin. Please remember I said this V and this V have to be of the same size, not that. Yes. Now, non-ohmic conductors. There are some which say we don't need to obey Ohm's law. Who is Ohm? Okay. These are conductors which do not obey Ohm's law. There are some conductors. Yes, they are conductors, but they don't obey Ohm's law. Examples: thermionic diodes, semiconductor diodes, lamp filaments, the tungsten filament for the bulbs, neon gas, dilute sulphuric acid when you use the platinum electrodes, thermistors. Thermistors are very special actually for them. For them, when temperature increases, instead of their resistance increasing, instead of obeying Ohm's law, when the temperature always increases, for them again they just conduct more electricity. So we have gas at low pressure in a discharge tube. All these ones here are very rebellious against Ohm. They are non-ohmic conductors. They don't obey Ohm's law. Constant and yes. Now, when you plot a graph of I against V or V against I for any non-ohmic conductor, you don't get a straight line. Examples: look at a thermionic diode. A thermionic diode, the graph looks like this. Somewhere it's a straight line, it appears as if it's ohmic, but then at high voltages, no more current. The current becomes constant. Like even when you increase the voltage, the same current will flow. Then we have semiconductor diodes, the junction diodes. For them, you don't get a straight line through the origin. Here, so the steepness increases. The interpretation of that can be mathematical, and I believe you know that. Lamp filaments, the tungsten filaments, like the bulbs you have at home, I against V. You see, as if this part is ohmic, but again this portion is not, so it's non-ohmic. Neon gas, oh, there is a portion here, but again, somewhere there is an exponential increment. Now, the lower side is just an expression of the reverse in voltage. You remember voltage is a vector quantity. Yes, so that's why you have this side here. Dilute sulphuric acid with the platinum electrodes. There will be no current flowing until a certain voltage is reached. Non-ohmic. Thermistors. Thermistors will be ohmic. For a certain limit of voltage, but from a certain point, the current that will flow will increase exponentially. So thermistors are materials whose resistance decreases sharply as temperature increases. I told you that before. Thermistors can be used as thermostats to control temperatures of rooms, freezers, etc. So connecting them in circuits in circuits of monitors, okay, which monitor and control the temperature. Now you have to know that because for them, when temperature increases, their conductivity their resistance to electrical conductivity decreases. That means they allow more current to flow when they are at higher temperatures, so they can be used to control temperatures of rooms and freezers. So a symbol of a thermistor is just like a resistor, but then you cross through, and some thermistors look like this. Yeah, the diagram is very small, but I think you can see it. Okay, let's go ahead. Now, a gas at a low pressure in a discharge tube, it's ohmic for a certain region, then it's constant, current will be constant for a big range of voltages, and then again it increases, so that's non-ohmic definitely. Oh, we have some special conductors called superconductors. Superconductors are materials whose resistance vanishes when cooled to 0 Kelvin. For them, when you cool them up to negative 273 degrees Celsius or 0 Kelvin, they have no electrical resistance. That's why they are called superconductors. And they're often alloys. They are also passive resistors. Instruments or conductors which convert all the electrical energy into heat. For them, all the energy that comes into them, the electrical energy, they convert into heat. So those are called the passive resistors, and they are used mostly in flat irons, in cookers, heaters, etc. So the heat is due to the collision between moving electrons and the vibrating atoms or the ions of the metal. We shall look at the details of this part under the topic of heat. So what are the factors affecting electrical resistance of a conductor? I guess you must be knowing them from what we've discussed. You must realize that these factors are very simple. One of them is the length of the conductor. Number 2, cross-sectional area of the conductor. Number 3, temperature, and we want to go into details of each. You know very well that, like for example, the length of the conductor. The longer the conductor, the higher the resistance, and the shorter the conductor, the lower the resistance. Conductors, the reason why resistors actually are formed from wound wires, because when you increase the length of a conductor, you increase the electrical resistance. So resistance is directly proportional to the length of the conductor. Number 2, cross-sectional area of the conductor. The larger the cross-sectional area, the lower the resistance. It's like racing through a wide road. The wider the road, the higher the speed at which the car moves. So in the same way, electrons will find it easier to move faster through a thicker wire than through a thinner wire. And it's a reason why, if you look at like if you look at filament bulbs, the filaments are very thin, because when they are very thin, the resistance will be very high, and therefore they will heat up, because of the high resistance. So the electrical energy is converted into heat, and when they heat up, they become red hot, white hot, and they produce a light. So we get the bulb. Thomas Edison did that for quite a good number of months to come up with the bulb. We actually appreciate him for that. The lower the resistance, the smaller the... Okay, the point is simple. The larger the cross-sectional area of the conductor, the lower the resistance, and the smaller the cross-sectional area, the higher the resistance. So in simple terms, R is inversely proportional to A. Resistance is inversely proportional to the cross-sectional area. Now when you combine the two, you realize that because R is directly proportional to L and R is inversely proportional to A, so you end up with this expression of the two factors combined. Number 3 is what we call temperature, and we know that the effect of temperature depends on the material. So the resistance of a pure metal increases with increasing temperature. We all know that. When the temperature increases, then even the resistance will increase. The resistance of certain other materials, like we looked at some of them, the non-ohmic conductors, realize that some of them at high temperature, some of them, not necessarily for non-ohmic conductors, but we're saying the resistance of certain other materials like carbon decreases as temperature increases. There has to be an S here. Okay. And then the resistance of various metal alloys such as constantan and manganene is nearly constant when the temperature changes. So for them, constantan and manganene almost don't get affected by the changes in temperature. And the resistance of semiconductors such as germanium or germanium, silicon and selenium decreases with increasing temperature. For them, their resistances are funny. When the temperature increases, for them, the resistance decreases instead. So therefore, the effect of temperature on the resistance of depends on the material. The nature of the material matters. Okay, I will pause it here. Arrangement of resistors in circuits. There are basically two ways of arranging resistors in circuits, i.e. we have the series arrangement and the parallel arrangement. Straight into the series arrangement. So for series, that means you connect one resistor after the other. So you connect them in such a way that the same current flows through each one of them. And the PD across each of the resistors is going to be different. Better follow through here carefully. You can pause and listen again. You can rewind. So let's look at this example. Consider this example. We have a resistor here, R1. We have R2, R3. 3 resistors, and they are connected in series. So they are, in simple terms, what you call, they are in a line. They are in. If you look at the current that flows here from the positive terminal, like this. If the current is flowing through here, it will reach this resistor. If it's I, the same current will go through this, and the same current will go through this, and then it will return, and then the process continues like that. So we are saying that if these resistors are in series, the PD across this is V1, the PD across this is V2, the PD across this is V3. So basically this is explaining what I've just done using the hand. If I is the current flowing through the resistors, and V1, V2 and V3 are the respective PDs across those resistors, R1, R2 and R3 respectively. So the total PD is V is equal to V1 plus V2 plus V3. We all saw that, and by Ohm's law, each of those PDs can be written as IR. So that means that I is equal to R sorry, V is equal to IR, remember that. So IR will be equal to IR1, this is for V1, IR2, this is for V2, IR3, because the current is the same, so we keep writing I everywhere. And the remaining part is just mathematics. So we end up with, therefore, R is equal to R1 plus R2 plus R3. The effective resistance for resistors in series is therefore the sum of their resistances. Let's look at a simple example here. Find the effective resistance for each of the following. Roman 1, or number 1 actually. What's the total resistance here, or the effective resistance? I think we can do this together anyway. So we said R is equal to R1 plus R2. What is R1? 2 ohms plus R2, 3 ohms. So you end up with 5 ohms. Yeah. So we're done. Number 2. What is the total resistance here? What's the total resistance here? What's the total resistance here? Sorry, I need to change this thing. R is equal to, here we're going to have R1 plus R2 plus R3, because these are 3. So because they are in series, so just add them. Therefore, the effective resistance is going to be 4 plus 5 plus 8, which gives you 9 plus 8, which is equal to around 17. Yeah. So you end up with 17 ohms. That is the effective resistance. Okay, now let's go to parallel arrangement of the resistors. For parallel arrangement, the ends of the resistors are connected between 2 points such that 2 conditions have to be fulfilled. Number 1, the current flowing through each of them is different, so the current divides up or it splits up. Number 2, the PD across each of them is the same because they are connected between the 2 points, so the PD is going to be the same and is equal to the PD across the whole combination. Now look at this. You have 3 resistors, R1, there is this point here and this point here. So you have these resistors, you have this resistor, this one and this one. They are all connected. They are connected in parallel. Parallel means if these are the resistors, this is resistor 1 and this is resistor 2, connecting them in parallel means you just join them. You join them like this. Yes. So here we have 3, that means you can join and then they are like this. Okay. So we are saying here, by the way, how do you get the effective resistance? What's the total resistance here? Remember, this current I comes here and then divides up into I1, I2, I3. That means I is equal to I1 plus I2 plus I3 plus I3. Now, the total current flowing through the whole combination is I equal to I1 plus I2, I3. So by Ohm's law, remember I is equal to V over R. So remember the PD is the same across each of the resistors. So we are going to end up with, where there is I, the first I here, we are going to put V over R. Where there is this I1, we are going to put V over R1. For I1, where there is this I2, you will put V over R2. Where there is I3, V over R3. And you realize V is common. Factorizing it out, the V will cancel. You're going to end up with 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Therefore, the reciprocals of the effective resistance R is equal to the sum of the reciprocals of the individual resistances in parallel. Note that statement. You can pause, rewind, and listen again. So note, for two resistors in parallel, you're going to have 1 over R is equal to 1 over R1 plus 1 over R2. And therefore, the LCM here is R1 times R2, which we have written here. And if you divide this by that, you'll have R2. This by that, you'll get R1. So you'll end up with 1 over R is equal to the sum over the product. Now, if you get the reciprocal of this, that means when this goes up and this comes down, this will also go up and this part will come down. So we'll have now the product will be up and the sum will be down. Therefore, for two resistors, if you want to get the effective resistance, if they are in parallel, just get the product over the sum. Examples. Find the effective resistance in each of the following diagrams. The first one. So we have two resistors. They are in parallel because here, if the current comes in here, it's going to split up into I1, I2. The moment it splits up in different directions, that means we have what we call a parallel arrangement. Remember, we said here R is equal to what? Sorry. R is equal to, I need a stylus, people. This is disturbing me. R is equal to, because they are in parallel and they are only two, so you write R is equal to R1 times R2, which is a product, over the sum. R1 plus R2. So what is R1? R1 is a 2. R2 is a 3. So your R is going to become 2 times 3 over 2 plus 3, which becomes 6 over 5. And what does that give you? 6 over 5 is the same as one whole number, 1 over 5. And 1 over 5 is same as point what? 0.2. So you get 1.2 ohms. Okay. The second one. What about if there are 3? By the way, the other first one, this one here. Okay. The first one, this one here, you would still attempt it by just saying 1 over R is equal to 1 over R is equal to 1 over R1 plus 1 over R2. You would still end up with the right answer. So let's look at this. Now when there are 3, the special formula doesn't apply. So you'll have to go to the fundamental formula. These are 3, so we are going to say 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3, which becomes 1 over R is equal to 1 over, what's R1? 3 plus 1 over 4 plus 1 over 1. And what do we get? 1 over R is equal to, LCM is 12. 12 divided by 3 is a 4 times 1 is a 4 plus 12 divided by 4 is 3 times 1, you get a 3 plus 12 divided by 1 times 1, so you get 12. When you add up together, you're going to end up with 1 over R is equal to, when you add all together, that is, I think, 29, yeah, no, 19, sorry, yes, 12 plus 7, that's 19 over 12. Therefore, R over 1, which is R, I just get the reciprocal, sorry, R is equal to 12 over 19. 12 over 19 ohms. You can get that in decimal points. Number 3, we have this kind of setup. So for this kind of setup, For this kind of setup, all you have to do is, because these are in series, these are also in series, so simplify this diagram and have this kind of setup. I don't have a stylus, I repeat, please. My diagrams appear weird because I don't have a stylus. So now when you combine 3 and 5, what do you get? Because they are in series, you get 8 ohms up, 8 ohms, and then down when you combine you get 5 ohms. Okay, therefore our R here, remember now they have become 2, is going to be product over sum. R is equal to R1 R2 over R1 plus R2. That means we are going to multiply 8 times 5 over 8 plus 5, which is going to be 40 over 13. Number 4 is yours. Please do it. You pause and you do it. Number 5 similarly. Number 5 is also yours. So we shall continue from there. Thank you very much. May God bless you. I remain Monday Dennis, the physics teacher in Uganda, East Africa. For God and my country. Be safe. May God protect you during this pandemic era.